black holes with the legacy survey of space and time. So today we have 7 very exciting talks. Before we get to them, just a few reminders. So one for the speakers, remember that you have 18 minutes and then there will be 6 minutes for questions. I will give you a warning when there's 3 minutes before the end of your talk. For the audience, please remember to, unless you want to speak, to maintain your mic muted. Also you can write questions that you have in the chat, or you can raise your hand and I'll try to follow the questions that come along for the questions session. And then at the end of the 7 talks, we'll have about a half hour for discussion. If you want to post a topic for discussion, feel free to write them on the chat here on Zoom or on the AGNSC channel on Slack, so we can keep track of them. So without further ado, let's go to the first talk of the day by Demetra de Cicco, structure function analysis of VST-COSMOS AGN. Go ahead.
Thank you, Roberto, and thank you for allowing me to present this work. So you can hear me, right?
Yes, perfectly.
Okay. So hello, everyone. Today I will present you some very recent results from our analysis of the structure function of AGN in the VST-COSMOS area. This is still an ongoing work and is actually the 6th in a series that is dedicated to AGN variability studies. And in previous works, we put effort into the development of a reliable and effective method to identify AGN via optical variability in the deep drilling fields, and specifically in the COSMOS field and the Chandra Deep Field South, with the ultimate goal of deploying this method over future LSST data. And so we managed to prove how optical variability is able to return highly pure samples of AGN candidates, how the completeness with respect to a reliable selection of confirmed AGN greatly improves when you have an extended baseline. In our case, we started from 5 months and then had 3.3 years in the end. And also we switched to a machine learning based approach starting from a traditional one. And also in our last work, we provided a lower limit expectation for the number of AGN that we expect to find over the 18,000 square degrees that will be covered by the LSST main survey via optical variability, of course, and based on our dataset. And we expect to find more than 6 million AGN. Now, with this work, we analyze the structure function of the AGN, of a sample of AGN that we know in the VST-COSMOS area, and we select them through a number of different diagnostics. So we also compare the results that we obtain in order to investigate possible differences among different selections. And also we extend the analysis to the analysis of possible dependencies of black hole mass and accretion rate, going to magnitudes fainter than most of the previous works from the literature. Indeed, our magnitude goes down to 23.5 in the R band, and so this means that we are extending the analysis to approximately 1 dex in terms of luminosity, meaning that we are investigating a new domain of the domain of the most common quasar and an AGN. So the dataset we use, well, we've been using this dataset for quite some time now, but still it is very useful as a test ground survey for AGN variability studies in view of the LSST, because we have a baseline of 3.3 years. So, okay, not as long as the one that we will have with the LSST, but still very useful for studies for the first years. Okay, for predictions for the first years at least. We also have a high observing cadence. You can see we have 3 bands, but most of our work so far have focused on observations in the R band because it has the highest observing cadence of 3 days. And also we have a considerable depth, and it is worth mentioning that our R band single visits have a depth that is comparable, that is basically the same that we will have for LSST visits. So basically in the past we selected AGN, we gathered together several catalogs of AGN to confirm our AGN candidates, and so now we combine these catalogs and we put them all together and obtain a sample of 677 AGN selected through at least one of these properties. So we have optical spectroscopy, and so we will have type 1 and type 2 AGN, X-ray selected AGN on the basis of the X-ray to optical flux ratio, AGN selected on the basis of mid-infrared colors, the well-known Donnelly diagnostic, and also our selection based on optical variability via a random forest algorithm. So you can see all of them here in this Venn diagram. Of course, the areas here are not quantitatively significant. And you probably noticed that most of our sample consists of X-ray sources. This is because for Cosmos, we have a very good X-ray coverage, which is, of course, not always the case. And also, I would like to stress that for 91% of our sources, we have a spectroscopic measurement of the redshift. So the idea is to investigate the ensemble variability of our samples of sources, the 6 samples that I mentioned. So here, I wanted to show what we obtain from each light curve, because for each light curve we have a minimum of 27 and a maximum of 54 points. And so for each source and for each light curve, we compute the magnitude difference corresponding to each rest frame time difference. And you can see all these points here in gray. We're talking about almost 10 to the 6 points. And then you see the bin structure function up here. There are several definitions proposed in the literature, and we chose to use this one by Clement et al. Proposed in 1996, as this is particularly sensitive to the problem of outliers. As you can see, we average the magnitude difference and then we square it. And so in this way, we reduce the weight of the outliers. As for the noise, well, we estimated it in 2 different ways. Basically, the noise is what you are supposed to observe when your sources are not varying. So as a first step, we selected a sample of non-variable sources. You can see them here in red. Basically, I took sources that I had inspected for my latest work, sources that show no sign of variability in none of the catalogs that I know of in Cosmos, basically. And so I selected this sample. It consists of almost, I think, 900 sources. And I obtained a structure function. So basically, what I see should be just a variation due to noise. Also, if you compare these variations in red here to the very first points of the structure function, they are pretty much at the same level. And you are not supposed to detect variations for such short timescales unless you're lucky in detecting very short variations, because basically the structure function we're looking at here, we're talking about a very, very short timescale. Here we have 10 days, so we don't expect to see significant variability. And basically I compared the two methods and found the same order of magnitude for the estimate of the noise. So I wanted to show, first of all, the structure function for the cleanest structure function that I obtained, that is the one for type 1 AGN. Okay, somehow we expect this. You can see blue and red points corresponding to 2 different thresholds for the sample, because I wanted to see what happens if, I wanted to see if there is any dependence, any change in the shape of the structure function related to the depth of the sample. And as you can see, there is nothing significant here, no significant change. I computed the slopes for what can be considered as the linear region here, while I excluded these points, again, because we are talking about very short timescales here. And so the error bars are larger. Typically, you don't detect large variability, while I excluded the points that you see here because the drop you see is not real. It's due to incompleteness issues. Basically, we don't have enough data to adequately sample these timescales. So,
Demetra, one thing,
yeah.
note that we do not see your pointer. It seems like you're trying to point to a specific thing. So just a note. You
don't see it now?
I don't see it, at least, no.
Okay, this is weird. But okay, I think we can do without it. So we don't waste time. Is that okay?
Absolutely, go ahead.
Okay, so on the right, you see the sample of AGN selected via optical variability, and you see that pretty much we have the same thing. And this happens because basically the sample is highly biased towards the type 1 AGN, as you can see from the blue caption here. 75% of the sources are type 1 AGN. So these samples allow us to retrieve the cleanest structure functions, and we computed the slopes for the linear regions, and they are also consistent with several results obtained from the literature. I just show a couple of them in the bottom of the slide. And on the other side, if you look at the structure function for the type 2 sample, the sample of type 2 AGN, you don't really see significant variations. You see larger error bars, and I plotted this linear, I mean, the slopes that you see here were obtained, just show an example, and correspond to the same time, to the same baseline where I computed the linear relation here. But of course, you could, in principle, fit the whole set of points with a line, okay? The thing is that here we have the dominant contribution from the host galaxy, and so this prevents us from detecting variations from the nucleus. So when you start including this type of AGN into your sample, so you have a heterogeneous sample, you will see your structure function changing. Indeed, for the mid-infrared sample, for example, we are still dominated by type 1 AGN, we have 60%. But you can start, if you look at the third, the fourth point, you see that you still don't see much of a variation. And things change even more if you look at these samples that are pretty much the same, except for like 70 sources. And here, the linear region is not as clear as it was before, and this is because we are including more and more type 2 AGN in our structure function. Okay, now, once we have our structure functions for the various samples, we are interested into investigating possible relations with black hole mass and N-to ratio. So, first of all, we have estimates for almost 40% of our sample, as you can see from the table, and this data come from the works in the blue box on the right, on top right. And I showed the distribution of black hole masses for each of the samples, but then in what follows, I will drop type 2 AGN because they don't vary significantly. And I drop also X-ray AGN because you can see that the numbers are basically the same as the full sample, except for 4 sources. Here I wanted to show a comparison with some of the previous works investigating these relations. So you can see that we are covering a broader range of black hole masses. Actually, in Paula's work of 2018, the range is very good. The issue there is the depth. So that's why we are working with a different data set now. But anyway, we are covering, we are retrieving lower black hole masses here in this work. So basically, we take each of our 4 samples of AGN and compute the median black hole mass, and based on that, we split each sample in 2. Okay, and so we plot their structure function. I showed just one sample, the full sample here, because it would have been too much, okay, putting all of them together, too much confusion. And you can see 3 different tests corresponding to 3 different depths. Again, because I want to see if there are significant changes in the shape and the slope of the structure function when we go deeper to fainter magnitudes. In the bottom panels, you can see a zoom in onto the linear regions for each test, and you can see it from the plots themselves or from the numbers here for the slope estimates, that basically we don't see significant differences. We cannot say that there is a relation between the amplitude and the black hole mass, but what we see is that the points corresponding to higher black hole masses are systematically higher with respect to the arrow ones, to the red ones, okay, corresponding to lower black hole masses. In order to verify if this depends somehow on the Eddington ratio, we do a further test. And so we select a very narrow range of sources corresponding in the surrounding of the peak of the Eddington ratio distribution. We do it for each sample, and we limit the analysis to the sources that fall within that range. So again, we take these sources, we split the sample in 2 based on the median black hole mass value, and then compute the 2 structure functions. And here in the panels on the right, you see solid lines for the 23.5 threshold and dashed lines for the 22.5 threshold. But again, we come to the same conclusion. Okay, so no significant relation is detected here. Then we do a similar analysis for Eddington ratios. Again, I drop X-ray sources and the type 2 sample. And here I showed the comparison with the works I mentioned before, and you can see that we are also retrieving sources with lower Eddington ratios in this case. And we do the same thing. Basically, we split each sample in 2 based on the median Eddington ratio. And so here you can see the region of linearity for each test with 3 different magnitude thresholds. And you can see that in this case, there is a mild anticorrelation between the Eddington ratio and the structure function. So you can see that for lower Eddington ratios, we generally have a steeper structure function, even though this is not something striking. Okay, we don't have such a difference. What we notice is that when we go towards brighter magnitudes, so when we have brighter thresholds, the distance between the 2 structure functions seems to increase. This is something I am still investigating at the moment. And we did the same test as before, but in this case we selected a sample of sources with a black hole mass that can be considered roughly constant, and come to the same conclusion that the editor ratio might be a mild driver for AGN variability, as we see this anti-correlation with the variability amplitude. Now, since several works in the past have investigated AGN, the structure function of AGN, even though to shallower depths, we wanted to compare our results with them. So, for example, there are a series of works by McLeod et al. Of 2010 and 2012, for example, where they first compute a damped random walk model fitting SDSS quasars in the stripe 82, and you can see it in green here, as well as on the left in the original figure. Also, you have in blue in both figures the best fit broken power law from the work of 2012, where they have a selection of several thousands of quasars, tens of quasars actually, tens of thousands of quasars with at least 2 observations for which they compute a structure function. And in red you can see our sources, and you can see that the trend is pretty much the same, even though there is a shift between these 2 sets of data, but this could basically depend, first of all, on the different data set, different instrumentation that we use. Also, there are works that investigated the possible relations with black hole mass and editor ratio. For example, we have the work by Zim et al. Of 2016, where they have a 4-year baseline, 4-year observations with gaps, and so they investigate 2 different baselines, one of a few months and one of 1-3 years, in different magnitude, different bands, sorry, and they come to our same conclusion. So the editor ratio seems to be the fundamental driver of AGN variability, while they don't see any significant relation with the black hole mass. And also in the work I mentioned before, Sanchez et al.
You have 3 minutes left.
Okay, thanks. In the work I mentioned before, by Sanchez et al. 2018, they find the same thing. They find that the most important relation among the ones that they analyze via multiple linear regression is the anti-correlation between the amplitude of variability and the editor ratio. So this is just a summary of what we obtained so far. Please keep in mind that this work is almost over, but not yet. Okay, so basically we found that the shape of the structure function is not significantly affected by the depth of the sample of AGN, and so our findings basically confirm the results that were obtained in past works where the samples were typically 2 magnitudes shallower than ours, 2 magnitudes brighter than ours. Okay, type 2 AGN do not seem to be a suitable sample for this kind of study, maybe because their variability is intrinsically different, maybe because we just are not able to detect it. And we confirm also results about the dependency on the editor ratio, and while we don't see anything significant regarding the black hole mass. In the context of LSST study, this is a lower limit expectation for the first years of the main survey, and we proved how optical variability returns a very clean structure function. So this is to keep in mind, because it will be, it's much easier to get light curves than it is to get spectra with this survey, and so we could in principle take advantage of this to get clean structure functions and study the structure function of AGN with LSST data over much longer timescales, which is also something that would be really useful to investigate the anti-correlation with the editor ratio and see if it gets any better, sharper. Okay, I think I can stop. Thank you.
Great, thank you very much. Are there any questions for Demetra? So I have a quick question. So on the when you showed the cloud of points for the structure function, there was a kind of a very clear gap at around 1.8 days.
Yeah.
Why is that? Yeah, right. Again. That plot, exactly.
Yeah, sorry, this slide drives me crazy because it's really heavy, the plot. Okay, yeah, here, you mean here, right? Well, this depends on the fact that we have 3 observing seasons for this data, and there is a gap between them. In particular, between the 2nd and the 3rd season, we have a large gap of several months. And so basically this is reflected here there is a lack of data in this region, and also the bump that you see soon after that depends on this, because there is a slight difference in the quality of the data, and it is reflected in the structure function.
Perfect. Thank you very much. Gordon, go ahead.
So, I mean, this might be more of a thing for the discussion, but Matthew Graham mentioned yesterday, so the need to sort of get away from structure functions because of the inherent time asymmetry and that sort of being inconsistent with the data, right? And we see that too in the work that we've done. And so I guess the question is, is that necessary here? And my thought is no, right? If you're just looking for, trends in black hole mass and Eddington ratio, it's probably, not important, and that the structure function is fine. And I'm just curious to get reactions to that.
Well, yesterday I missed Matthew's talk, but now thanks to Niel who shared the slides right before I could, I could follow most of it. So I know that in principle it could be useful to use a different approach. I know Matthew's ideas about Amphanov walk also. I know his work of 2014. So there are different ways you can use to parameterize ensemble variability, and I think this could be meant just as a starting point, because this is something that actually we started some time ago and we set it aside, and now that we had a decent baseline and a lot of observations and data, we wanted to see what happened at a zero order basically. But in principle we could try and use a more sophisticated and less traditional approach for this. So this is meant to be like a starting point for this kind of work.
Great, thanks.
Paolo?
Yeah, I just wanted to clarify. You said there's no correlation with black hole mass, but then you say that the variability amplitude is larger for larger black hole masses. The slope doesn't change, I guess, but the amplitude does?
Yeah, that's right. The slope does not correlate there's no significant correlation with the slope, but the amplitude, yes, it changes. It's systematically higher for sources with higher black hole mass.
Okay.
Yeah.
And okay, thanks. And I'm just wondering, have you tried breaking it up into subsamples, like with Ann Bauer in that 2009? We tried taking low mass AGN and high mass AGN. It looked like there's a hint that the slope did change, or that there are different types of AGN. Not everybody looks the same, and by putting together these big samples, you're blurring over individual distance differences. But at the time, we didn't have enough statistics, so we couldn't say anything. But so people compute these mass averaged structure functions, but the sources could be quite different types, changing look. I don't know. It's all mixed together. Do you think that's a problem, or what to do for LSST?
Okay, so you suggest separating the sources based on additional properties. That's what you're saying, right?
Yeah, exactly. Yeah.
Mm-hmm. Yeah. That I haven't done that yet, but basically that's what I was doing. I mean, I was investigating different properties because I started from the two that among the most commonly surveyed properties. Okay, black hole mass and Eddington ratio. But then there is a lot to investigate still. I should investigate other dependencies, and so yeah, this is something I will do for sure.
Matthew?
Yeah. Nice work, Demetra. I think somewhat in response as well to Paolo's just comment, you're looking at 650 data points here, total sample size. So the ensemble is pretty much about as good as you can do. I think into LSST, when we've got 6 million to work with, there will be much better discrimination into subgroups and whatnot. But I would take with a pinch of salt any such results that might come from a sample size this small. I think my other comment was, have you broken them up by luminosity in any way?
Not yet.
No.
No, that's one of the things I should investigate. Also, our possible wavelength correlation is on the list.
Well, I mean, the standard statement is that less luminous AGN shows stronger variability. And so if the less luminous is showing stronger variability, and you're also seeing a higher amplitude variability with mass, it'd be interesting to make sure that your results about Eddington are consistent with that relationship.
Yeah, I will do that. And I understand what you said about the sample being small, but still, I mean, this is a starting point, and I know it's just
I'm just saying. I mean,
it's deep. The good thing is that it's deep. So what is new here, or pretty new at least, as far as I know, is that we are going much deeper than most of the other works. Then yes, it's just 1 square degree, and it's not 18,000.
Which is why which is why I think the luminosity would be interesting, because it would be interesting to see how far the luminosity function you're actually probing with this.
Yeah, that's on my to-do list. I was actually just playing with this a couple hours ago.
Okay.
Thanks for pointing it out.
Thanks. So there's time for a very quick question. I guess Maurizio, you wrote something on the chat. I don't know if you want to mention.
No, I was just wondering about the request to split in additional parameters. And I was wondering what parameters would we have, for instance, for LSST, because of course color is one of these, but if you need spectral features, then they will not be available for all of the source or X-ray luminosity and so on. So it depends, this limits what we will be able to do.
Yeah, I know. So every time you split it into further subsamples, you reduce the size, and in the end you will have to not for the full sample maybe, but since we are already talking about not such a large number of sources, we should be very careful, I think, with this. But in principle, some more analysis can be done here before stopping.
Thank you very much, Demetra. So let's move to the next talk by Andjelka Kovacevic about the LSST observing cadences for measurement of AGN variability. One thing, so right before you start, so two things that I forgot to announce at the beginning of today. So one is if all the speakers would be able to, after their talks, send the PDF of your talks to Niel Brandt, so we can compile them and make them available to science collaboration. And if it's too large, you can just send a link so he can download it. And then the second is that we're planning on taking a group picture today, right before we go on for the second break of the day. So around 1:10 p.m. Eastern time. So the idea would be that everybody turns on their cameras if you can, and we can take a picture of everybody that is assisting to the meeting. So with that, let's move on to the next talk. So please take it away.
Dear colleagues, it is on behalf of our team, it is our honor to meet you all. Special thanks to organizers, to also chairperson Roberto Assef for nice introduction. As an LSST in-kind contribution team, we are grateful to AGN-SC for allowing us to report on preliminary results from pilot version of cadence node related to understanding how much the statistical properties of ordinary variability, such time lags, periodicity, and structure function in LSST AGN light curves could be affected by the different LSST cadence strategies. AGN-SC feedback on what we can do to improve in that regard is more than welcome. In this task, we try to follow AGN-SC roadmap recommendations, which is upgrading now and implements the challenging vision of handling millions of LSST AGN light curves, as we already heard in the opening talk by SC co-chair William Brandt. The broadband photometric reverberation method by Chelush and Daniel can utilize such data to estimate the mass of numerous AGNs. For objects at higher redshift, careful choice of filters is required, since some spectral lines can be found at the border of the two filters, as elaborated by Panda et al. Because of this, in this report, we will be located at the redshift around 0.05 if otherwise is not stated. Our pilot cadence node focuses on the AGN-C roadmap theme called ordinary AGN variability without detecting the supermassive black hole event horizon to test constraining the mass of supermassive black holes, measuring dimension of the Broadline region, and detecting possible periodic signals of supermassive binary black hole systems in simulated LSST AGN mock light curves. For simulating LSST AGN light curves and injecting periodicity, we used continuum light curves represented by Demetra random walk model. We choose it for implementation in the pilot version because DRW is the oldest example of Gaussian processes in AGN LC modeling. Moreover, since Kozlovsky et al. In 2010 proposed the DRW model for quasar selection, MacLeod et al. Moved the field of the quasar variability studies from a handful of objects to statistical study fitting over thousands of quasars. Due to reasons given in excellent reviewing talk by Matthew Graham yesterday, the next upgraded version of our cadence nodes will include LC models, such as Gaussian processes with exotic additive multiplicative composite kernels, such as in this real world example. Then LC parametric models for single and binary black holes, as it will be presented in the next talk by Simic et al. And finally, data-driven models based on conditional neural processes, as our early career scientists, Iva Hajdinjak and Isidora Janko, will present it tomorrow. Here, we recall that Wei-Xiang Yu offered yet another model of AGN LC in his nice talk yesterday. To test the LSST observing strategies, we created a bench scale artificial set of objects based on 20 cadences from OBSIM 1.5 to 1.7 realizations. Their designations are listed in the last column of table. These OBSIM ramps comprise different observing strategies, for example, between 50 to 90 epochs per 10 years, such as in U and Z band, about 1 kilo to 1.5 kilo epochs per 10 years, for example, in DDF, and about 200 and more over 10 years, mostly in G and R band. For these artificial objects, the redshift is kept as low as 0.05 due to reasons mentioned. And we perform time lag and periodicity determinations using our methods and compute parameters and statistical measures for each light curve, such as fractional variability, general photometric error of the light curve, time scales of interest, time lags and periodicities with their measured errors, and general light curve sampling time. Both input and measured time scales are within 3 sigma mutual distance. Some injected periods were larger than LSST observational time baseline, so we couldn't measure them. This turns out each heterogeneous mock LSST light curve into raw feature vectors in the parameter space. And we assume that these feature vectors for the ensemble of light curves populate some manifold. To estimate the statistical influence of LSST cadences on measuring variability observables, we constructed 2 metrics. For the first metric, we combined statistical features for each light curve, the relative formal error of measured time scales, the fractional variability relative to the measured general photometric error of light curve, the ratio of observed time scales, such as time lag or periodicity, and general light curve sampling time. Plotting these combined features in 3D for an ensemble of light curves in G and R band, we aggregated them. Then we try to find a hyperplane that will describe this manifold's gradient and possibly connect these features. The metric coefficients C1, C2 tell us how to compare variables on a given ensemble of objects. The figure displays the PDF of time lag and periodicity metrics performance for G and R band objects, and the smaller relative formal errors and their medians are more likely to occur for the R band. This is not surprising since the R band contains almost 3 times denser cadences, enabling light curves to capture more information. As the next metric, second, a structure function can inherit oscillations from precursor light curves. We were particularly interested to estimate LSST cadence effects on SFs, and therefore we adopt the simple first order SF method on light curves with the underlying oscillatory signal. As seen on the upper plot for sparser cadences, calculated SF will lose oscillatory information. Contrary, finer LSST cadences preserve underlying oscillatory signals. Metric related to SF is simple and estimates deviations of SFs based on OPSIM cadences termed gappy light curves from reference SF obtained from idealized one-day homogeneous sampled light curve. We calculate these deviations curves for objects in different redshift bins and average the deviations curves for each time scale and redshift bin. Two-column figures present PDFs of SF metric for each LSST OPSIM cadence summed across the SF time scales left and redshifts right. The peak of each distribution shows the most likely metric value, that is deviation, from the idealized SF. PDFs are marked with different colors for each LSST OPSIM cadence, so that blue corresponds to the LSST OPSIM cadence with the smallest deviations. These are more suitable, while the redder color distincts the OPSIM cadences that have the highest deviations. They're less suitable. The metric in the R band shows that LSST SFs are more coherent with more minor deviations than those in the G band along the SF time scales, and similar behavior can be seen across redshifts. Based on these two metrics, we find that using LSST data from sparser bands, such as U band, for time delay and periodicity detection is not ideal. Instead, we favor using algorithms on LSST cadences having more than 200 observations per LSST operation lifetime, such as in G and R band. Also, we find that LSST observing strategies which provide good sampling frequency, about 1 kilo epochs per 10 years, are particularly suitable for AGN variability observables, and rolling cadences, about 200 observations, perhaps wouldn't cause any problem in calculations, since coverage of sparse sampling periods could be enough for machine learning algorithms. Here we briefly present just pilot results of toy simulations of different transfer functions of accretion disk in different LSST bands and their effects on simple toy light curves. We designed two types of toy light curves for driving source emission single Gaussian with a mean of 0 and standard deviation of 1 day. And it illustrates how the peak positions shift when convolving with the time delay transfer function of accretion disk. We used drivers represented also by the sinusoid model to show how the oscillatory signal is distorted. And we generated multi-band light curves based on LSST UGRIS bands. We choose different quasar redshifts, black hole masses, but Eddington ratio and accretion efficiency about 0.1. And we calculate the corresponding disk size in each LSST band accounting for the quasar redshift. We displayed the transfer functions in each band of the top panels with the mean of these distributions labeled as vertical dashed lines. And as a result, the new curves are shifted in time and deviated from the original. This is also seen in sinusoids, specifically in their amplitudes. Also, for equal mass supermassive binaries, we apply coupling formalism devised by Wang, and it is demonstrated how coupled disk transfer functions of Kacht, Horne, and Winkler in different LSST filters alter driving source of single Gaussian and sinusoid. The following steps will involve the Gaussian processes curves, conditional neural processes, and light curves from other models. Using these types of curves, we will try to expand on the task of continuum time lag measurements. To end, I would like to highlight that even our pilot cadence nodes show that denser sampling OPSIM realizations are superior to sparser in producing smaller relative errors of infrared timescales and less deviating structure functions. We believe that good algorithms can overcome lower sampling, as we have seen in an excellent talk by Matthew Graham. However, scarce cadences containing less than 80 time instances, such as in U-band, perhaps are unpromising for extracting more refined information from AGN light curves. The next level of our notes will include different LC models on larger LSST cadence sample. As a team, we are grateful for AGN SC guidance, and we will continue to cooperate and implement AGN SC recommendations. Especially, we appreciate points given by Matthew Graham yesterday, which are very, very important for our future works. So, ladies and gentlemen, thank you so much for your interest and attention.
Thank you very much, Andjelka. I see Maurizio already has a question, so please go ahead, Maurizio.
Oh, thank you. Very nice talk. I was wondering if through your simulation, you can suggest some way to compensate for the sparse sampling, since in any case, we will have that in some bands, the cadence will not be ideal. So can we at least correct on average for these effects?
As I do believe is actually, you are absolutely right, Maurizio, that we will have a very great challenge in with these light curves, and to actually use more sophisticated approach, as has been shown to us by Matthew Graham. I think that yesterday's talk by Matthew Graham is some kind of prophetic pathway for us, that to use actually more data-driven algorithms. However, I am not positive about very scarce bands such as U or Z, where there are about 30 to 40 points per 10 years. So I don't know, maybe for some sciences it could be enough, but I don't know what we can do in such cases. So I don't know, Maurizio, have I answered your question?
Yes, in part, yes. I was hoping that at some point we can make some assessment of what are the biases that we introduce, so that we can at least compensate to the first order. Then, of course, probably different structure function or different model will be degenerate, and so it's not easy to reconstruct what intrinsic variability is.
Yes, I agree. That is really important, specifically if structure function is used for many tasks. We are not expert in structure function and its characteristics, but what we are interested in structure function is yet another method for measuring periodicity, and it was utilized for some other studies, I think in blazars or something, to detect periodicity. So from this point, we have been interested in structure function.
Thank you. I guess Matthew Graham put a comment on the chat. It says it depends whether it's a question of imputation or prediction with sparse sample data.
Could you repeat once again, Roberto, because I didn't catch, I'm sorry.
Perhaps Matthew can ask the question, because I'm
yes,
not sure I fully understand what
Yeah, well, I mean, again, it's, maybe this is something we can save to this discussion session, but I think it's just along the lines that filling in, let's call it, it's missing data, but it's not missing data. Sparsely sampled data, how to handle that in the U-band particularly. There are data generative models that we could use if they were coming from a data-driven perspective. But it depends whether I think it depends very strongly on what we're trying to constrain and whether we're trying to impute data or predict data values. And I think as you're seeing with the results that you've shown, that that sort of thing could be useful, but it could also be very heavily dependent or biased on what models you're putting in.
Yes, absolutely. I absolutely agree with you. And also we have We have colleagues who are working on big databases and on problems of imputing missing data into them. So actually, as somebody said, if each AGN would be the same, but not individual variable entity, actually our science will be, how to say, science and not the art. So I agree with you that utilizing many models, comparing them and statistically decising among their outputs, and it will be very, very important. And perhaps algorithms will evolve much more on higher level than now.
Oh, thank you very much. Unless there's any more questions, I think we can move on to the next discussion. Oh, to say that on Slack there is, okay. Okay, that was for Demetra, the Cicco. So I guess so if you want questions for the talks, let's put them here on the Slack. Let's try to put the questions for the discussion session. Just to, I do not have enough eyes to keep track of everything. But cool, thank you very much. So let's move on to the next talk then by Sasha Simic on simulating light curves of supermassive black hole binaries.
Okay, do you hear me?
Yes, can hear you very well.
Okay, thank you very much. First, I would like to thank I would like to thank the organizer for giving this opportunity to present our work. My collaborators are Luka, Popovic, Andjelka Kovacevic, and Dragan Ilic, and we together working on developing the model for simulating light curves of supermassive black hole binaries. At the beginning, I would like to take a short reminder about the structure of the AGN, particularly in the central part of the AGN. We strongly believe that in this object there is a supermassive black hole which is surrounded by the accretion disk, and that disk is the main source of huge amount of radiation we can detect. We are interested in working with objects which has not one but two black holes in its central part, and the justification for that kind of the object is taken from the collision, for example, for a collision of galaxies, where at the end it can evolve in a super galaxy with binary black hole system in its core. The distance between the black holes can decrease during time and passing from kiloparsec to subparsec scale. We can observe that in kiloparsec scale we can make the observation, for example, using some of the existing telescope system in radio domain, but in subparsec scale the direct observation is not possible, not just because of lack of resolution of our telescopes, but also because and mainly because the central region is hidden from direct observation by dense material, which doesn't allow photons to pass through. So the detection of such object is not possible by direct observation, but using some other techniques like spectroscopic analysis or observation of light curves. We strongly believe that dynamics of the internal dynamics of the binary system can somehow imprint the periodic oscillation in light curve of that object, and that can be analyzed and monitored by the LSST telescope, which is very suitable for observing of that kind of object. That presents main motivation for us to develop a simple model which can give us the light curve and spectra for analysis and maybe observational proposal, etc. Our model is recently published in Motley Notices, and it is still under improvement and construction. The model is based on the proposition that there are two black holes rotating around common mass center, and both of them contain a accretion disk around the black hole, and additional surrounding gas and matter is redistributed in a way that both black holes contain the broadline regions surrounding the accretion disk and the black hole. The orbit of the binary system is thought to be basically eccentric, so the distance between the components can vary during the orbit, and that presents some kind of variation. We'll see later how can that be incorporated in our model. We propose also that the broadline regions around the black holes are mostly coplanar, and that they does not interact. Contrary to that proposal, accretion disk of black hole does interact, and it is not just interaction between the black hole and its own accretion disk, but it is interaction between the accretion disk and the opposite black hole in the binary system. That is also can produce some kind of variability, possibly through temperature, to perturbation of temperature profile. We assume that orbital velocities in such compact systems are high, so we include in our model relativistic beaming from the Oratio in 2015. Model also proposed that there is additional circumbinary broadline region, that is the region surrounding both black holes and their broadline regions, and it is also proposed to be coplanar. Dimensions of the circumbinary broadline region is determined by the emission from both black holes, and it can be computed by using some of the empirical luminosity size relation. Its property is that it is stationary, it doesn't move, so discrete spectrum it produces, for example, we use H-beta line in our study, it is of fixed wavelength and doesn't suffer the shift, which is more connected for the broadline region 1 and 2, which is movable. And that is the main geometry of our model. But additionally to this, we are interested in studying the additional geometry and configuration, and that is very similar to our model. It can be stressed to be as a special case for our model. It is based on the idea that there can be a system with a very low mass ratio, and that means that one component can be much smaller than component than another component. In our model, we designate the M1 as a smaller component and M2 as the more massive component. And what happened then, since the difference in mass is great, then the component 1 is much more agile than the component 2, and it will end up in M1 rotating about around M2, and during this rotation it collects all material from the external, which is coming toward the central parts, and just a small amount or nothing passing toward the component M2. That causes that our system loses the Broadline region 2 and have just Broadline region 1 and circumbinary Broadline region. Additionally, since the all material falling toward the black hole 1, the accretion rate of black hole 1 is in super Eddington regime, while accretion rate for component M2 is very low. This particular case can be also studied with our model. Dynamics of the system is covered by Kepler laws, and we introduced that basically orbits are eccentric, and we define the orbits of black holes with three angles. That is the inclination angle, it is argument of descending node, and the orbital phase. We can get the radial velocities by the solving Kepler equation, and for some arbitrary system with mass ratio 0.1, the radial velocities are presented in this figure here. It is important to discuss the accretion disk, and the accretion disk seems to be similar as in the single black hole AGN, and it is geometrically thin and optically thick disk. It can be thermalized and emit radiation as a black body. We assume that temperature, that there is a temperature gradient, and it is directed from inner parts, which are more hotter than the outer parts, and the temperature profile can be described as in the single black hole AGN. However, due to the interaction, there is a perturbation of that temperature profile, and we include that perturbation in our model by this member of the equation for temperature. And also, it is not just that the temperature profile is perturbed, but also the accretion rate is also changed due to the tidal interaction. So we include this additional member and assume that the accretion rate is dependent on the orbital phase of the system. Both of these those effects are included in our model, and the total luminosity of the accretion disk is acquired by superposition of all parts of the disk. The temperature profile of the disk of both black holes can be seen here in this image. The dark arrows show direction toward the very center, and we can see the perturbation of the temperature profile is not so small and can somehow in some particularly in higher mass cases in high mass system can be significant and induce additional variability on the light curve. H-beta line is used in our model to study the Broadline region properties. We want to define the line, so we need to find line intensity, line width, and shift. H-beta line is composed from the components, and there is a contribution from all three Broadline region parts: the Broadline region 1, 2, and circumbinary Broadline region. We proposed, and it can be found in several empirical relationship between Broadline region size and continuum, that intensity of line can be directly dependent on the size of the Broadline region, and the size of the Broadline region can also depend on the luminosity from accretion disk. So that is connected by using this luminosity size relation given by Caspi and Wu in 2005 and 2004. And we thought that we proposed that Broadline regions are mostly virialized, and use virial theory to compute the velocity distribution and line width. Additionally, line shift is mostly Dopplerian, and we avoid gravitational shift since it is very small in comparison to the Doppler shift in this kind of objects. Now, in some cases, for example, when there are higher masses of the components, the Broadline region size computed on the basis of the luminosity size relation can be oversized, and can oversize the entire binary system. So it is not, for us, it wasn't realistic enough. So we introduced, we proposed that a Broadline region surrounding the black holes are reduced in dimension. And we propose that that reduction is according to the Roche lobe. Here is, you can see the reduction, moment of reduction of dimension of Broadline region.
You have 3 minutes left.
Oh, okay. Time's passing. Okay, then just to clarify, this is important. We use to compute the intensity from the regions, Broadline regions 1 and 2. We are using the luminosity size relation, but we artificially reduce the luminosity from these regions, and we use these cases for 70, 50, and 30% in favor of, for example, Broadline region connected to the black holes, and the rest of the emission coming from the circumbinary Broadline region. And that is very interesting, since it is giving us the possibility to study the influence of different regions in the composite light curve. Just quickly to show the results of our simulation. For example, here is simulated H-beta line, and for different parameters, this is mass ratio, and this is the order of mass magnitude. As you can see, for example, in this case, we can generate the emission from black hole in continuum and superposed H-beta line for black hole 1, black hole 2, and circumbinary is dash dotted line here presented, and solid line present the composite line from all these regions. I will just passing through. This is the mean line profile with RMS is also something we can compute here our model. We added here the white noise. Additionally, variability of continuum F and the H-beta line can be explained and computed. We here added the red noise using by formalism given by Kelly et al. In our special case, which I explained earlier, We can also generate the mean line profile and RMS value, as well as H beta line shift and line asymmetry, given in these graphs here. H beta line light curve variability and continuum light curve variability with complete white noise and red noise implemented. And at the end, I would like to say that we are currently working on this, on developing of this model, and we're trying to write it in the Python code to be publicly available. It will have the first page where you can choose the parameters, the input parameters and effects you want to include. And also there will be additional controls for choosing what type of data you want to have. Is it in the form of graphs or is it in form of files? And that will be all from me. Thank you very much.
Thank you very much, Sasha. Are there any questions? So I have a quick question. So when you showed the geometry with the circumbinary BLR,
This is
yeah. So because the BLR will basically be influenced by how the gas is illuminated, shouldn't the shape actually replicate kind of a peanut shape around the two black holes, right? That it's actually a peanut that is moving with the black holes themselves.
Yes, okay. Well, in this model, we are trying to simplify things. That's what you are talking about. Maybe can implement it in some further step. But for the simplicity, we keep that these areas, Broadline regions, are of the coplanar and circular shape. And maybe in some further work, it could be improved for that shape you're proposing.
Okay, yeah, because I think that shape, the nice thing is that it would predict a change in shape of the line that is periodic at the same periodicity of the orbiting black holes.
Okay. Thank you very much.
Thank you. If there's no more questions, let me quickly check the Slack. But if there's no more questions, we can stop here for the break. And so we'll be back at 11:55. So we're running a little bit ahead of schedule. So we'll be back at 11:55 in about 17 minutes exactly. So see you in a little bit.